Hi everyone. So in this video we discuss a strategy for handling the vanishing gradient problem, right? So because just to recap from last time, because we raise the same matrix corresponding to the parameters to a large power in a recurrent neural network, both problems of exploding gradient, if the norm of the gradient with respect to the parameters is large, right? So both problems of if the parameter matrix has a large norm, because both the back propagation and the forward propagation has a w raised to the t. So we have two problems that become very likely: the exploding gradient, and last time we discussed a computationally efficient way of dealing with the exploding gradient, which is the clipping of the gradient norm. That turns out to work well in practice, even if you clip the gradient norm element-wise, right? Even if you replace the exploding gradient by a random step. Now, a more tricky problem is vanishing gradient. Why? Because when the gradient vanishes, you really don't know which direction to move along, right? Because vanishing gradient means that the gradient direction is moving you in a direction where the coast would not change, right? So it becomes unclear how to move to the right direction, and basically something along the lines of like the analogous way to clipping the gradient norm by just increasing the magnitude is not guaranteed to do much, or is not really backed by intuition, because the gradient direction is the problem, right? So, and also another thing is that what really matters when the gradient vanishes is that the gradient with respect to the hidden state, remember when we discussed the echo state networks and reservoir computing, the gradient with respect to hidden states, right, is the gradient that should have a consistent norm, because this is the gradient that is being back propagated, right? So for reservoir computing, the idea was that the eigenvalues corresponding to the the eigenvalues of the Jacobian matrix corresponding to the state-to-state transition, these eigenvalues should be close to 1. In particular, the maximum of them should be close to 1, but we discussed all of them is better to be close to 1, because that will make you learn along all the directions without one direction dominating the others, right? So why did we focus on that Jacobian in the echo state network? Because it is this Jacobian that gets multiplied by the gradient. So the gradient with respect to h of t times the Jacobian of h of t with respect to h of t minus 1 that's what will give you the gradient with respect to h of t minus 1, right? So this thing right here, that's what will give you the gradient with respect to h of t minus 1 of the loss function, right? So now let's come to this strategy. So what happens is that you basically regularize, and the condition of regularization is that you want the gradient after back propagation with respect to the state at time t minus 1, the norm of that gradient to be as close as possible to the norm of the gradient before the back propagation step, which is the gradient with respect to h of t. So that you are maintaining that when you are back propagating, you are not making a change to the norm of the gradient. Maybe you are making a change to the direction, but not to the magnitude, right? So basically you add a norm penalty, and that norm penalty is the summation of all time steps of, for each time step, we have in the numerator the norm of the gradient with respect to h of t of the loss times the Jacobian of h of t with respect to h of t minus 1, right? That will give you the gradient with respect to h of t minus 1 of the loss, divided by the norm of the gradient of h of t with respect to h of t of the loss function. You want that division to be as close to 1 as possible, right? And then you square, because you don't care if it's less than 1 or more than 1, you want to penalize both directions in the same way, right? So when I add norm penalty like this, a norm penalty meaning there will be a regularization coefficient multiplied by this function. If that coefficient is very large, then it's as if I am enforcing reservoir computing or operating in an echo state network fashion. If that coefficient is very small, then it's as if I'm not doing regularization at all, and I have the fully trainable hidden state approach, right? So the regularization coefficient is what will give you the flexibility by how much you want to approach the reservoir computing approach when imposing that penalty. Now that penalty will make you move in a different direction than the direction of the gradient that is vanishing. So that's important to note. When we deal with exploding gradient, we maintain the direction, but we clip the norm. When we deal with vanishing gradient, we are actually changing the direction to another direction where the norm remains the same after back propagation. Sounds good? Thank you.